Yeah, thanks so much for the invitation, and thanks to all the organizers. This has been like such a fantastic day, and I've already learned so much and met so many interesting people. So yeah, really excited to be here. I'm going to chat today about some of my work and some of the broader work in the environmental policy space, thinking about how artificial intelligence is kind of changing the ways in which we make environmental decisions and the implications of this on environmental justice and equity. Okay, so probably most folks in this room recognize the top image, the climate warming stripes, a visual representation of temperature change over the past 50 or so years. And on the bottom is kind of an analogous representation of biodiversity loss over the same time horizon. And of course, these are deeply intertwined crises. So climate change is one of the main drivers of biodiversity loss. And healthy ecosystems are going to be critical to mitigating and adapting to climate change. And I like to start my talks with these two really simplified representations of these intertwined global crises because they've been incredibly influential at kind of communicating the urgency of both of these crises to both policymakers and the public. But of course, these are vast oversimplifications of what are really complex and spatially heterogeneous crises, both in the drivers of these crises. So here you can see kind of threats to species globally are not uniform, of course, as well as the impacts of these crises. Of course, global warming is not happening kind of evenly across the world. And while the crises themselves and kind of their biophysical impacts are quite complex spatially, so are the policies that are being put into place to address their drivers and kind of come up with solutions. Of course, we have kind of global agreements and conventions, the UNFCCC for climate change and the Convention on Biological Diversity for biodiversity loss. But ultimately, these agreements are implemented by national and subnational governance agencies. So in the first 2 or so minutes, we've kind of built up this quite complex problem where we have multiple intertwined global crises. They're nested in space. And we have these complex policy landscapes where we have everything from multilateral agreements to subnational initiatives and even kind of local scale decision making. But we're also in an unprecedented time of information. We have satellites taking images of the Earth that increasingly find spatial and temporal resolutions. We have camera traps, acoustic monitors, things called flux towers, which kind of monitor, emissions from the ground. We have smartphones, all of these sorts of technologies that are helping us monitor our ecosystems and the ways in which they're changing. And increasingly, we have the computational tools to leverage all of these data into insights. Again, like monitoring how our ecosystems are changing. And this is really where the majority of AI has been applied to the environmental domain, really thinking about how we translate raw data into more derivative data products that are more easy to use. Again, really doing primarily ecosystem science in this space. And my own work in the kind of ecosystem science space really started from an observational perspective. So how can we use global remote sensing data to understand things like the contributions and the potential of landscapes to mitigate climate change and address biodiversity loss. Specifically, a lot of my work was thinking about how different integrations of land management practices, so trees and agricultural landscapes or otherwise, might contribute to climate mitigation, and whether or not we can think about the socio-political dimensions that drive some of the patterns that we see from space. So in this case, we were looking at kind of different integrations of trees into agricultural landscapes, both by bioclimatic regions as well as kind of socio-political regions. We can also use these observational approaches to infer policy impacts, which is a really cool application of computational tools to environmental decision making. So in this project, we were looking at kind of the impacts of policies in different subnational jurisdictions in the US and how well they did or did not kind of drive acquisition of conservation areas that targeted the most critical landscapes for biodiversity and climate mitigation. But we can also kind of take the opposite approach to what are really similar problems. Is like, rather than looking at them from space, maybe we can actually try to understand the mechanisms that are driving these patterns that we're seeing from space. And so there's a lot of really cool work in the environmental domain looking at how we can build simulation-based models to try to kind of reproduce landscape scale patterns. And so this generally falls in like realm of what we call agent-based modeling, which exists in a lot of domains. And computational tools have been, and AI really has been super influential in allowing us to model more complex decision-making processes that are existing in these sorts of landscapes. So can we better model agents that are making forward-looking decisions, strategic decisions, social decisions, rather than having like agents that are seeded with really simplified decision rules, which is kind of historically how this work has happened. And this is a really cool space because we're then not constrained to kind of the policies that have been put into place to date, but rather can like play with the total action space of policies. So we can design interventions and see how they might play out in a simulated world. I mean, there's a lot of cool work and a lot of work to be done kind of combining these two things. So can we combine the observational approaches and all of this large-scale information we have about patterns of land use specifically and or like other environmental interventions with like mechanistic understandings of how these processes play out and how kind of humans interact with their environments on really localized scales. And so that was kind of like the first half of my PhD work, but I got really interested in kind of how we can go from all of these system insights, kind of traditional like social environmental systems work, to actually coming up with the decision strategies themselves. So kind of my early work in the social environmental systems space was really about simulating the systems and not really about the mechanism design itself. So like, what do you do then with all of this kind of complexity of simulation? Do you just throw like one potential policy at it and see what happens? Or can you actually be strategic about designing those policies and those policy interventions in the first place? So how can we use AI and or other computational tools for environmental problems, combining both this ecosystem science or social environmental science with decision science, which is going to be the second part of this talk. A lot of my own work is really focused on the Global Biodiversity Framework right now, which is this global agreement that was signed a couple of years ago, outlining 20-something global targets, pretty focused on biodiversity. Some of these are really charismatic that you might have heard of, like things like 30 by 30, which is a global agreement to protect 30% of lands and seas by 2030. But there's also a number of other targets in this framework, restoring 30% of degraded lands, but also specific targets about kind of strategically implementing these policies. So these area-based goals are not the actual end goal. Of course, the actual objectives are mitigating biodiversity loss and climate change. And this is a really interesting case study because, of course, there's these global targets, but they're ultimately being implemented by sovereign countries that are making their own decisions and kind of deciding on how they want to contribute and how much they want to contribute to these global goals. So I'm going to turn to the EU for a little bit of a deep dive, not too deep, on a specific project kind of looking at some of these questions of like, how can we use computational tools and AI to come up with strategies for implementing these policies. And I'm going to zoom in on the EU for a couple of reasons. Partially because they've committed to a biodiversity strategy for 2030 that is really well aligned with these global targets. They've committed to conserving 30% of lands and waters by 2030, as well as restoring 20% of lands more recently with the Nature Restoration Regulation. The EU is also a really interesting case study because, of course, there's kind of EU-scale targets, but then individual member states are contributing differentially to meeting these targets. And there's a lot of questions about like how countries might collaborate and the implications of different kind of cooperative agreements to reach these larger scale area-based goals. Does each member state do it individually and equally, like each protecting 30% of their internal land, or can there be trades of these sorts of goals, and how much benefit might we realize from cooperation? Okay, alongside biodiversity, of course, we want to go back to climate change. Yeah, we're kind of simultaneously, of course, in a climate crisis, and the European Union has committed to pretty ambitious climate targets as well. The Fit for 55 package is kind of a suite of interventions that are trying to reduce greenhouse gas emissions by at least 55% by 2030 in the EU. And a lot of these have land-based implications. So a lot of bioenergy production and otherwise that can have negative impacts on biodiversity. And so we have to think about kind of weighing the land demands of climate mitigation with some of the biodiversity conservation targets, and whether or not these are in conflict with one another. So there's been a lot of work in this space on doing land allocation problems and spatial optimization problems for conservation prioritization, for restoration prioritization. Increasingly, a lot of work on what our production demands are going to be and how they're changing into the future. But these are often done naive to one another. And so a lot of my own work is thinking about how can we actually plan all of these in concert so we can have more holistic approaches to land allocation planning. Underlying these decision-making problems is, of course, a whole bunch of data. So we want to maximize the biodiversity benefits of our policy interventions. So a lot of the work that kind of underlies these decision-making processes necessitates large-scale models of biodiversity distributions, carbon distributions, as well as kind of how changing landscapes or land interventions might impact biodiversity and carbon, as well as a lot of information on production demands and the ways in which production demands are changing. I'm not going to go into the details of any of this specific work, but if you have questions, I'm happy to chat about it afterwards. Okay, so we can throw all of this into kind of optimization models and come up with nice strategies for meeting all of these targets and understanding when and where they are not or are feasible. And we can do this under a whole suite of different scenarios. So things like different value weightings, slightly different policy implementations, understanding, again, the impacts of burden sharing or responsibility sharing for these policy targets under different production demands or under different climate mitigation scenarios. And we can come up with quite nice maps that can show us what our 2030 landscapes might look like under one or a number of these different scenarios. So this is just one kind of set of kind of scenarios, I guess. And each of these production, conservation, and restoration maps are, of course, broken down by different land cover types so we can keep track of the impacts on species and carbon. Okay. Okay, so then we can also, this is kind of nice because we can look at the potential outcomes of these policies if we have spatially explicit implementations of the policies themselves. And we can see how these things like weighting different objectives or burden sharing actually kind of quantitatively might impact what we realize as benefits from these policies. Okay, so we're asking this question of where. It's already quite complex. But actually, these are policies that are being implemented over kind of decadal horizons. They're 2030 targets. They're not targets that are going to be met in one swoop. So rather than going from a current landscape to kind of one single future landscape, I think that there's a lot of questions to be asked in the space of how do we make sequential decisions over these long policy horizons, and is it possible to do this spatial and sequential decision making in such big action spaces? You can't use the same methods that we used here to do that. That's just not in scope. So what can we do? We can simplify the system. That's often how we've made sequential decisions or sequentially strategic decisions in the environmental domain for quite a long time, really since the 70s when we founded this term called adaptive management in the field. But now we have all this information, all this complexity, and we're investing so much in monitoring our ecosystems and learning about all this complexity. So if we can't use it in our decision-making processes, then why are we investing so much in learning about it? it's probably not going to be integrated into human heuristics, and so what? Of course, computer scientists have been hard at work coming up with really impressive algorithms for designing sequentially strategic decisions in really complex and high-dimensional spaces. And so some of my work is thinking about whether or not these tools may or may not be applicable to problems of sequential decision-making or adaptive management in environmental domain problems. Really thinking about whether or not we can apply these tools to what is traditionally an adaptive management process, which you can see if you do anything in like the reinforcement learning space, it looks quite similar to what you learned the first day in like reinforcement learning and or just, control space. But yeah, can we replace some of these model-based and really optimization-focused approaches with reinforcement learning and overcome some of the limitations that have existed in this space? Things like non-identifiability of our models, so environmental tipping points, for instance, non-stationarity, or model misspecification, amongst a number of other things that we outline in this paper. And just to show an example, this was a paper where we looked at a system that had a tipping point or, an ecosystem collapse, and we showed that reinforcement learning algorithms were actually more apt at coming up with policies for managing these systems than our traditional kind of approaches at managing a simple fishery system. Okay, but of course, a lot of these algorithms have been designed in the context of games or really well-defined physical tasks. And now we're proposing to apply them to monitoring, manipulating, informing our environmental decisions, and even enforcing our environmental policies. What could possibly go wrong? If the rest of society has anything to say about it, actually a fair bit. Not to mention, a lot of these tools and their infrastructures are deeply embedded in the same industries that have driven these crises in the first place, and have larger impacts on already marginalized communities, which hopefully leaves us also with the question of whether or not AI will actually prove to be an engine of ecological modernization. Will it really propel us towards these more just and sustainable futures, or will it rather simply be an extension of our current extractive patterns of production, further entrenching environmental inequities? So how can we combine ecosystem science, decision science, and ethics and justice in the context of AI applications to environmental management? I think a big question that's come up a lot throughout today's meeting, which has been so interesting for me to hear about from other domains, is like, who has a say? Who has a say in these algorithms, how they're designed, and what they include or exclude? And this is something I'm super interested in and have been working a lot with a sociologist thinking about power dynamics and specifically accountability in reinforcement learning, but other AI more generally, applications to environmental policy. How these algorithms might shift not only decision-making power on the x-axis, but other dimensions of power. So agenda-setting power, world-making power. Who gets to decide what questions are even on the table in the first place, and what kind of features of our environment we include in those decisions. Of course, it's not only an issue of the tools themselves, so shifting from traditional optimization to more complex or opaque algorithms, but also the underlying data that drives kind of the outcomes of these algorithms. So if we think back to this restoration and conservation priorities example I showed earlier, underlying those, I really briefly mentioned that there's a bunch of models of species distributions, or just maps of where species exist or don't exist. And underlying those is, of course, a bunch of biodiversity data or species observations. And if we look at global observations of biodiversity, we see that even if you're not an ecologist, this is not what you think of when you think of a map of global biodiversity or global species distributions. This is our global database of biodiversity that's most widely used. There's 3 billion observations, give or take, in this database. And rather than kind of global macro ecological patterns, we actually see global macroeconomic patterns. We have a lot more information in high-income countries. And if we zoom into one of those high-income countries, the United States, that's where I'm coming from, we also see disparities within the data in those countries. We can see cities and roads, areas that are accessible, kind of lighting up. And this isn't like hugely problematic. I mean, it is, but like we can adjust for it in some of the models that we create to model species distributions. But if we look at these cities, this is Los Angeles, we can see the legacy effects of racist policies. So we have almost double the amount of biodiversity data in neighborhoods that were not historically segregated in the US. We can see armed conflict and colonialism and when, where, and by whom our data are collected. Which hopefully leaves us all asking the question of how these social, political, and historic dimensions of our biodiversity data impact not only the ecological insights that we derive from these data, so where species are, where we have the highest potential for implementing policies, but also the distributional equity of the decision strategies that come downstream from these ecological insights. And what can we do about it, particularly in the context of like the urgency of these global crises? Of course, we can collect more data, and we need to collect more data, of course. But that's not as simple as it might sound. First, we're never going to like collect all of the data. We're always going to have some sparsity in data. Second challenge of that is like some of the most underrepresented areas are also some of the most like surveilled communities. So it's not always such that you can just go into a community and be like, we're going to collect a bunch of biodiversity data because this is a spot that is like a huge gap in our biodiversity data. Actually, like that's really complicated from like a community consent perspective. So we can correct for the biases, as I mentioned. We already do this when we take our biodiversity data and come up with ecological insights. So maybe we correct along social and political dimensions, and we overcome some of the implications of these biases on the downstream decisions. A couple of problems with that as well. The first of which is like a bias of datafication. So if we take a like purely technological or statistical approach at correcting for these biases, we can only correct really along the dimensions that we can easily quantify, which is a very subset of the social dimensions that exist within these data. The second problem, which I think is a bit more fundamental, is that people, our politics, our economies, our histories are major drivers of ecosystem composition. So we don't always want to like flatten out some of these like unevenness in our data because they're actually giving us indication for like how people and our processes are impacting ecosystems. So things like armed conflict, for instance, have a huge impact on ecological systems. And if we just like correct for that unevenness in the data, we might not actually be able to understand how these sorts of human things are impacting species and the such. And so we kind of explore this idea in a short policy form piece with a really interdisciplinary group of people, really encouraging the community to think about these global databases and these global problems in the local context within which these data are produced, really thinking about data not only as a technical infrastructure, but really as a social infrastructure. And a lot of my ongoing work is being done really closely with a political ecologist, thinking about like why these patterns in our data persist and shift, not only combining like quantitative approaches to understanding socio-political and historic dimensions of biodiversity data, but doing a lot of interview work with data providers, managers, and curators to try to understand like what sorts of interventions might be most effective in this space. And just to conclude, I'm really interested to continue to chat about how and where computational tools can help inform equitable and robust strategies to meet biodiversity and climate targets, and when and why we should use caution. Hopefully engaging across scales, all the way from local scale to global scale understandings of both these crises, but also the solutions to these crises, as well as engaging across disciplines, which has been like such a cool part of being here over the past few hours. Working with everyone from sociologists and political ecologists to computer scientists and ecologists. And with that, I want to thank a whole bunch of collaborators who have helped me with all of this work and really been influential. And yeah, take questions if I have any time.